All right. Well, sorry for the delay. Yes, my name is Italo, and aside from the name, I'm not from Italy. I'm from Brazil. And I work in Berlin in a company called Lycon. I basically live in Berlin for a while, and I work in a company also called HelloFresh in N26. Um, I work at Lycon as a head of technology, and one of my favorite topics is about failure, right? How we deal with failure in a software, in a system. And today we saw a lot of different things, a lot of different strategies from the Bill Kennedy's keynote and also mission critical systems. But how do we design systems for the unexpected? You never know when something will fail. In a distributed system, that becomes even harder. So that's why I want to bring us today a few of the standards that we use across distributed systems that can help us a little bit on deal with failure. But before we jump into that, I'd like to tell you a story. I am a huge fan of aviation. And if you think about aviation, we have a lot of airplanes going on right now in this exact moment in the air. And they run systems, right? They have this mission critical system that they cannot fail, otherwise people will suffer. Just to give you an idea, we had 39 million flights up to this day just in 2019, which is a lot of flights. Out of these flights, unfortunately, we had 8 deadly crashes, which doesn't seem like a lot, around 39 million. But if you think about it, that's 233 deaths, which is unfortunate. Does anybody here know how many of these 8 crashes were caused by a software failure? By any reason? 8? 1? 1. There was 2. Okay. So from the FAA in the US, they reported that 1 crash was caused by a software failure that was actually audited by them. And that's, I think most of you know, the 737 case where the MAX is going on right now. That's a software failure. It's not only software, there's human error on it as well, but the software was the main cause, right? But if you think about it, like 1 crash out of 39 million flights that happen throughout the year actually was caused by software. And there's a reason for this. The reason is there is a design system in the airplanes that are actually designed for failure. And it's not that airplanes don't fail. They actually fail quite a lot. We just don't notice. And we want to apply kind of the same concept to our systems, the systems that we design. There is something in the airplane called ELMS. That's an electric load management system. And this system was designed in 1993, if I'm not mistaken. And in 1993, they actually designed a system that is able to load shedding and actually have timeouts inside the system that if something does not respond, system will automatically do something. Those are concepts that we use most of all today in our distributed systems. And one example is the battery of an airplane. So an airplane has around seven batteries. It just needs 1, but it has 7 fallbacks just in case something happens. And still, if the whole ELM system goes down, you still have a mechanical battery going on. So when the air goes through the turbines and actually go through the engine, you can still generate power because air generates power, right? So you have that backup, like that mechanical backup, just in case something goes wrong. And when that happens, when a system fails, they keep running only the essentials in the airplane because you have to fly the plane down to the ground safely. So that's why they keep the essentials. This is a very important concept when you think about applying to a software. Imagine your systems today. Can they run only with the essentials? Can they fail everything else? If they can, that's great. If they can't, that's why you're here, and we are going to talk about it. So I like this quote a lot. Resilience is a requirement and not a feature. Many times I remember that I jumped into these product meetings, and you go there and you actually have to preach to the POs like, can we have a circuit breaker? Can we actually have some time to apply a few of these concepts in our systems, and so on and so forth? If the PO is cool, you're fine. They're going to allow you. But if you're in a tight deadline and you have to deliver your product, you're going to struggle a little bit trying to put a few of the concepts that we're going to show you today. But that's why I like it to face it as a requirement and not exactly a feature. If you have a very good and experienced team, this is going to be super useful. So we're going to go through a few things today. We're going to go through latency control, load shedding, isolation, self-healing, and traffic control. And we're going to start with latency control. There are a lot of different strategies that you can actually apply latency control to. But today, I'm going to talk about one that Bill Kennedy mentioned in the keynote. And I was like, yeah, cool. I already used the hat, which is pretty close to him. Now he talked about timeouts. Great. Timeouts, that's the first one. So we have different kind of timeouts. We have client timeouts, and we have server timeouts. The one that he showed earlier was a server timeout. So client timeouts. How can we do client timeouts? Well, any language probably supports it, but Go has a very nice way of dealing with it. This is a simple way of how you can do a client timeout, right? Very simple. On the HTTP client, you can simply set up your timeout. That means when you're calling a service, another service, an external service, it's going to time out in that specific time. You can be a little bit more complete as well. You can have dialer timeouts. You can have TLS handshakes. You can have response header timeouts. So you can set all of these by using the native HTTP client, which is great. And we should be doing this. It's a lot of boilerplate, but it's still worth it. It's going to save you a lot of time. But it's interesting, though. In the latest version, we have something in the Go 1.13. We have something called HTTP new request with context, which you can see right there. That is basically allowing us, if you look at the client that I'm creating, I'm not setting a timeout anymore. That's because I'm setting in the context. If you set in the context, the request will actually do a cancellation, and you can use the context later on throughout your application that will be canceled in case a timeout happens. That's a little bit better. I'm going to show an example in a bit in code, and we are going to see this a little bit in action. So this would be a client timeout, a very simple client timeout. And a lot of times, we just forget to use it, but I do recommend that we start using this more often, just in case your external dependencies start to fail. You're going to avoid a lot of cascading failures. Then we jump into server timeout, which is basically what Bill's talked about. We have some of the timeouts up there, which are read timeouts and write timeouts, which are the very basic ones that we should be setting when creating HTTP servers. Idle timeouts, this is really important in terms of idle connections being there, and you don't want them to, well, basically keep running. And you have the read header timeout. Normally, when another application is calling yours, those timeouts are actually going to kick it in. They're pretty useful. Cool. Circuit breakers. Who here actually uses circuit breakers on a day-to-day basis? That's a few people. Cool. All right. So circuit breakers. I remember when I was working at HelloFresh, there was one of the SRE people. They were like preaching circuit breakers every single day to us. I think we have a few HelloFreshers here, and they actually remember that. They preach like, we should have circuit breakers. We should have circuit breakers. Why? The main reason is you want to avoid cascading failure. That's basically what you want to avoid. Cascading failure is service A depends on service B. Service B depends on service C. If service C fails, service B will fail, and consequently, service A will also fail. And you want to avoid this because it's super hard to debug, especially if you don't have observability in your system. Then it becomes a nightmare. So in Go, there is a library, and it's a very interesting library called, Hystrix is the library that actually is managing the whole circuit breaker system. Hystrix is a pattern that was created by the Java community, basically. And it's a very smart pattern that can be implemented in Go, and it was implemented with this library. This library is used inside Heimdall. Heimdall is a HTTP client, a little bit smarter than the normal, the native HTTP clients that Go actually provides. And it comes with circuit breakers, retries, and also a few fallbacks. What do you do if a circuit opens? So the way circuit breaker works is service A depends on service B. Think about that. And service B starts to fail, right? So service A is going to do a few calls. A few of them are actually going to fail. You're going to have a threshold. So if you see on the configuration up there, we can set some thresholds there. We can say the timeout. We can say the max concurring requests that can actually go into that server. And we can actually say the error percentage threshold. So here I'm saying only 20% of the calls can actually fail. If they come to fail, then the circle will open. When the circuit opens, no calls are going to be done anymore to service B until the sleep window actually kicks in. That avoids overloading the service B, which is going through probably an overload problem. And that makes your application avoid the cascading failure as long as you know how to handle this. So Hystrix here actually provides you a little bit of insights, like what can you do when it fails? You can fall back to something else. You can actually tell the users, hey, we're going through an outage, a problem, and you don't fail the transaction. So it's a pretty nice strategy. Hystrix also brings us this interesting dashboard. It's not out of the box, but with Docker Compose, you can quickly bring it up. And you can see how the circuits are actually playing around with. So you can see if they are closed or open. You can see some of them are closed. And with the circuit breakers, you have a little bit of more insight about how your calls are going on. I'm going to show this example also in Grafana, which makes a little bit more sense. But this is basically the standard circuit breaker dashboard that comes with Hystrix. But circuit breakers are nothing if you don't know what to do after the circuit opens. You actually want to do some retries probably. You want to make sure that if your service was having an outage or just an overload problem, after a while, you should probably be back on, and then you want to retry. But you don't want to do that yourself because you're going to be busy doing something else. You want your system to actually retry by itself. In the same library, you can actually set the retry strategies. So there are many types of retries that you can do and you can implement yourself. The most normal one is the linear retry, right? So you're going to have this retry timeout, and when the circuit opens, it's going to retry after a period of time. So it's going to retry, let's say, in 2 seconds. And then it's going to retry again, and retry again until a threshold of retries, and then it's going to stop. This is cool. But normally, a service don't come up like after 6 seconds, after 3 retries of 2 seconds each. So you want to do a smarter kind of retry, which is called backoff, right? The exponential backoff. That means if you call a system and it actually stops responding, it's going to try in 2 seconds, and then in 4, and then only in 6, and so on and so forth. So you give you a little bit of more time so the service can actually breathe. So in this library, you can write your own retry, or you can use the built-in ones, which are pretty solid. Cool. So load shedding. Load shedding, I think most of us use, even without knowing, which is load balancing, right? We use load balancing. We just saw in the previous talk. ALBs is one of the strategies. We have the ELBs as well for whoever is on the AWS world. But basically, that's what a load balancing does, right? It's this. It's making sure that your request is load balancing across your instances of the same application. But there is something else which is called outlier server host detection. This is implemented, well, Nginx has it, and also a few other applications also implement this, like Traffic has it, and Kong. This is basically making sure that when the load balancing is happening, if service B, well, one of the instances of service B actually goes down for whatever reason, it kicks off out of the load balancer and makes sure that on the mapping, it can only connect back to the 2 healthy instances. If that instance that was before actually having some problems, it will kick back in the same algorithms, and now you're going to have the 3 instances back on. That's a fantastic feature that normally is overlooked by us because it's done for us, right? So, but you can implement that in Go as well. I do not recommend. It's a lot of trouble, and it's not that simple to implement. But if you want to, it's doable, and there are a few examples that I'm going to show. Cool. Isolation. So isolation, another story time. Bulkheads. So probably most of you know the Titanic, right? Titanic, the big ship. Good. So Titanic went down in, I don't know, 2000, that would be nice, right? 1912 or something. And that's basically because this was supposed to be nicer. Okay, this is a nice gift. So the Titanic hit an iceberg. And the architect, if some of you watched the movie, there was an architect saying, after a period of time, the Titanic will go down just because those four containers actually were hit by the iceberg. That's a bulkhead. Bulkhead comes from the ship, the naval industry. And the bulkhead is just a container, right? Like you have a pool of these stripes right there, and they should contain the water. The problem in the Titanic was there was a design failure, and the bulkhead didn't really work because the water goes up, and if you see right there, the water goes up and passes through the level, like the floor of the Titanic, goes to the next one, and the next one, and the next one. Of course, after a while, there's too much weight for the ship to actually hold it, and then it breaks in the middle, and then it goes down. That's why the Titanic actually sank. The bulkhead pattern that we use today in software comes from the same concept. You actually want to make sure you isolate your thread pools. In our case, Go routines. So the same library that I mentioned before, the Heimdall, make sure that you have a pool of Go routines when you call a service. So let's say that you're calling service from service A to service B again. Service B is having a problem, but you actually have concurrent requests into your application. So you have 1,000 requests happening. And one of the services have a problem, as you saw before. One of the instances have a problem. But your whole application is not going to stop because the other two are working. And concurring requests, only a few of them will actually stop. That means just part of your application or part of the requests that you're serving are actually going to stop because they are split across different Go routines. And that's basically how the bulkhead works. So bulkheads are super important, but also it's transparent to us, as long as you use a library to do it. If you use the native HTTP client, you're not going to have bulkheads out of the box. You have to implement that by yourself. With the sync pool, you can also do some interesting magic. And it all will make sense in a bit when I talk about self-healing applications. Health checks. Another question, who here has health checks? All right, good. That's quite a lot. Now, who here actually have health checks that will do something similar to this, where you can say what is required for your application to be running and what is not required for your application to be running, but it has to be there. It would be nice to be there. So in this case here, I have a DB checker, right? This library is from InVision. It's an interesting library because it standardized the way HTTP code is returned in your /health or your /status endpoint. So basically what we're doing here, we're creating a pinger, so a checker pinger, which is basically just a ping to the database, right? So we're creating this instance, and we're making sure that we add them to the checkers. So here, there is, in a constant time, in an interval of 3 seconds, we're going to ping the database just to see if it's alive. If it's not, I will show you what's happening. But then we have another check, another external dependency, which is Google. I mean, if Google goes down, I don't care. My application still can run. Maybe a few of its functionalities are not going to run as it's supposed to be. But this is why I do fatal false right here, because this will generate this. If everything is OK, you get this standard response. You're going to see AMPQ here because I took the screenshot from another thing. But basically, this will show you a standard response. And that's a 200 right there. That's normally used by load balancers. That's normally used by like Kubernetes or Nginx load balance and reverse proxies to make sure your application is healthy. If things are not so good, but your app can still run, so the Google example, you're going to have these. It's still a 200, but you're going to see there that we have number of failures. This allows you to have external monitoring systems actually checking if your application is healthy, which is still can serve requests, or if you should be kicked out of the load balancing algorithm, or we should maybe put a maintenance page or something like that. And that's basically what shows you. So it gives you a 500 in case your database goes down, because then you actually avoid the load balancers to even route traffic to your application. So you're avoiding the cascading failure and the overload in your service way ahead of time, which is pretty useful. And of course, it keeps a standard that you can add this to your logging system, which also helps a little bit on how you can monitor this. So health checks are amazing for that, and they're pretty trivial to implement. Now, there is something also interesting when we talk about self-healing applications. So if any of you already dealt with event-driven systems, that's when the challenge comes, right? Event-driven system from Martin Fowler, that's basically, we have many standards of how we can, create these event-driven systems. We have Kafka, which is a stream. We have RabbitMQ, which is a queue. Essentially, we have Iron, and so on and so forth. And that's all good until you have problems in that specific provider, in that broker. So the outbox pattern, here's an example. So you have a service A that actually publishes messages to Kafka, right? It's pretty common. And then you have consumer A and B. Cool. What happens if your Kafka goes down? You shouldn't, right? You should have a very resilient Kafka cluster. But it can go down for whatever reason. What do you actually do? How do you make sure that you don't lose these messages, right? So you're going to publish something. Think about a transaction in a bank, for instance. If you publish that to a Kafka and your Kafka is not there, what do? You lose the transaction. You tell the customer, oh, sorry, you couldn't make the transaction because we're down. You don't really want to do this with your customers. So there are many strategies, but one that I like a lot is called the outbox pattern. And what the outbox pattern says is, instead of publishing to Kafka directly, you actually just publish to your database. Now, if your database goes down, well, you probably have a bigger problem to solve, but you shouldn't have your database down. So it publishes to the database, and then you're going to have a sender. You're going to have something which is in a Go routine, or if you use another language, is going to be a consumer, which actually checks for every single new record that is in your database in a table specifically for the event, and publishes to your broker. You can have many different brokers. You can have Kafka, you can have Rabbit, so on and so forth. If Rabbit is down, no problem. Your transaction is done. It's already saved on the database, and I'm going to keep you retrying until Kafka is back up, and then automatically send the messages back to Kafka so your consumers can work. Your customers will probably face a delay, but the transaction will be made. And in Go, we have something like this. This is the outboxer pattern in actually practice. So we have a Postgres instance right there, right in the top. And you can create an outboxer instance where you actually set what is your data store, right? So you set your data store, so your primary data store. And then after a while, you set your event stream. Here I'm just putting the example as a AMQP, but you can use Kafka or Kinesis or any other stream. And then you have a check interval. That interval actually checks for new messages, like how often should I check for messages in the primary data store to send to Kafka or to send to RabbitMQ. And then you have this cleanup interval, which actually cleans your database, the old messages on your database. That's optional if you want to keep a history, but it cleans up just to make sure you don't have a lot of records. Imagine having, I don't know, 1 billion records in your same table, then you're going to have to shard, and it becomes a little bit complicated. And then you just send the message. Right down there, you send the message as a simple slice of bytes, and then you send it, and then it goes to Kafka or goes to RabbitMQ and so on and so forth. This is a very simple thing. Like the start point is where everything happens. So it's just a Go routine going on in the back, which actually checks for new messages and make sure to send to your data to your event stream. Cool. And yeah, so it's a library that I created in case you want to check it out. We use it at Lycon, and it's pretty useful. Cool. Traffic control. Rate limiters are probably the ones that are most common in traffic control. We just heard about an API gateway. API gateways are supposed to do rate limiting, but have you ever thought about doing rate limiting on your services internally, which is also a very interesting problem when you have 100 services and you have a lot of dependencies, hard dependencies, then you probably want to rate limit. You probably want to do quotas on your service to make sure you don't overload your service as well. We've been through that, and it's not fun when your service starts going down. So rate limiter is super easy. Also in Go, there are many libraries, but you can implement yourself because it's very, very simple. And you can have different stores, so a memory store or Redis store if you want to do distributed rate limiting, which is what Kong and what Traffic does. If you heard about Envoy, Envoy also does it as long as you have a filter for it. And it's pretty useful. That's the way you can actually limit requests coming into your services. So we've been through latency control, load shedding, isolation, self-healing, and traffic control, which is a lot of things. Imagine you actually having to do all that Bill already said, plus this, and then you still have to do your business code, right? That's a lot. And of course, because of that, we have other concepts in play. We have, well, if you have one service, that's very okay to do it. If you have 10 services, well, you still can manage, you still can try to standardize how you're going to implement circuit breakers and all of that across all your services. When you start having 100 services, you probably want to rethink. You don't want to do that for all services that actually come up in your company. With 1,000, which is the case of Spotify, well, it becomes unmanageable, right? If you change your circuit breaker library, if you're using the same language across everything, then things are going to start getting a little bit clunky here and there. That's why service meshes actually exist, right? Who here uses service mesh? Right, not too much. Who here knows what a service mesh is? All right, cool. For those who don't know, service mesh, it's basically something that is happening quite often now with orchestration systems. In Kubernetes specifically, we have Istio, which is pretty solid. And the service mesh will take out a lot of the burden from your app to make sure you can have all of these things that I just talked about without coding anything in Go or in your code at all. Because Istio will have that proxy for you just to make sure you don't need to code all of that. So I'm going to show you here like the same code basically for Istio. Let me just switch this to the side. One sec. Can you see it? Right. And all right. So we have this here. Is it big enough? Let me just make it a little bit bigger. There we go. Right. So these are the Go implementations, right? Like we have the circuit breaker as I was talking about right here. Let's just make this a little bit smaller. Maybe not. Yeah, forget about it. So we have the circuit breaker right here. And if I want to do the same thing in Istio, right? Istio is basically something that you install in Kubernetes. It was, in theory, it can be installed in any orchestration system. But it was mainly built to work in Kubernetes. And you can do the same thing, like circuit breaker-wise, with Istio just by doing this configuration file, which is not too much. So we have here an outlier detection, as I talked about it before. That means if the health check of your instance in Kubernetes starts actually failing, it will make sure that after one error, you can configure this, of course, after one error in an interval of 1 second, it will eject out of the load balancing algorithm of Istio to make sure it doesn't call that not healthy instance anymore. So in a very simple way, that's how you can actually implement right here circuit breaker, outlier detection, and retries as well. So we have a retry example right here for Istio, which is there, with a simple retry. So what is happening under the hood, right? Basically, you have your app. Think about your app. Think about your container. And your container is running your orchestration system, specifically Kubernetes. And you normally have a pod, right? And this pod just encapsulates your container. What Istio will do, it will inject a proxy in front of it. It will make sure that, not in front of it, but a side to side. And it will make sure that every call that you do to any external dependency, that could be a database, that could be a Kafka or RabbitMQ or Google, it will make sure that all goes through the proxy that Istio makes. That allows Istio to actually take that proxy and apply this kind of filters, apply these retries, apply these circuit breakers, and then it handles the failure for you. It actually brings you a little bit of metrics, which I'm going to show you in Grafana in a few minutes. And you can see how your system is actually behaving, which is pretty cool. And only with this configuration. In your code, you can use the native Golang library and then actually make sure that your code is clean and easy to understand, making sure that everything else is handling it. What is the bad side of Istio, right? Instead of doing in Go, what is the bad side of Istio? Think about a circuit breaker again. And in Go, you have the possibility to actually handle the fallback. If something happens, you can actually handle it. In Istio, if something happens with your circuit breaker, you don't have a callback in Go. You don't know that it's actually happening. You're going to get a simple timeout error. You can handle the timeout error, but it's a little bit tricky. So Istio is cool, but you got to be careful. You got to know if you really need Istio. It's not something easy to maintain. But it does help when you have a lot of services and you have an orchestration system. Cool. Just for the sake of time, let me actually put this back on. All right. Last topic, already talked about it today, was observability. And nothing that I talked here makes sense without observability. You have to have metrics. You have to have logs, and maybe not standard logs, as Bill said, but depending on your case, standard log makes a lot of sense, and especially tracing, right? You want a distributed tracing actually going on. There is a very cool library in Go called Open Tracing and Open Census, right? Those are two different libraries, and not many people talk about it in the community, which is a shame because that library is amazing. It actually makes you it gives you the possibility to have standard metrics across your application for HTTP, or if you're using gRPC, it gives you out-of-the-box metrics for all your HTTP servers. That is latency or round-trip latencies, or actually how many bytes you received and how many bytes you're sending, and so on and so forth. That allows you to have a better visibility across all your services in the same way. So this is an example with Prometheus. We are exporting here all the metrics of our code to Prometheus, so we create a new exporter. Just an example, I think a couple of weeks ago, or maybe a month ago, we've changed it to Datadog in our code. So we had a lot of instrumentation going on. We changed it to Datadog because we wanted to try out a few features of Datadog. And we said, all right, all we got to do is change this little Prometheus exporter, and instead of Prometheus, we put Datadog. And out of the box, it was there, right? Like we had Datadog metrics and instrumentation going on in the same exact way with the same dashboards that we already had in Grafana. We moved back to Prometheus for other reasons, but it was that easy. It's super easy to do it. The same, and then, of course, you get these standard metrics. I'm going to show you real metrics in a bit. Distributed tracing is the same thing. Here we use Jaeger, but basically it's the same library that actually provides that to you. And Open Census and Open Tracing is a very cool project that is not only for Go, it's standard across many different languages, like from Java to Clojure to PHP to, well, whatever you want. And they're finally starting the Open Telemetry initiative, which is amazing. The Open Telemetry initiative is combining these two things in a single library, in a single way for you to report observability across all your application in all languages. It's a great initiative, and it's coming soon. It's coming this year, hopefully in December, I think. And if you want to contribute, please go there. It's amazing. It's really good. Cool. So for the sake of time, I will end up here. Those are the slides in case you want to see it. The code that I showed, I didn't have much time to show, but designing for failure. And the coffee shop is an example with RabbitMQ actually going on, and what happens if you kill RabbitMQ. You're going to see the application actually behave in a different way. So just in case you want it, there it is. And I appreciate your time. Cool. I know it's almost lunch, but in case anybody has any questions, feel free.
Anyone?
Everybody's hungry. All right, cool. So thank you again and enjoy lunch.